Good morning. Really, it's an afternoon here, but better late than never. That's what I say. This is your class for day 30 of Coronachem. It was supposed to have been recorded yesterday, but I was traveling yesterday, so I'm doing it today. So today is Saturday, but this class is for Friday, May the 15th, I believe, for grade 12. Your homework was to do number 1433. Let me read you the question. Define the following symbols that are encountered in rate equations: a naught, t to the 1/2, at, and k. So a naught is concentration at the beginning, or times 0. I'm noticing now that the book puts the naught symbol on the outside. I don't think it's a big difference. You can put it right next to the letter either way. So concentration at the beginning, or times 0, is a naught. T 1/2 is equal to time till half of the substance is used up. It's a half-life, which is important in first order processes, and I mean it's also important in the second order processes. And there are two separate equations for dealing with those. Then there's A sub T, which is the concentration of the substance at any given time, and K is the rate constant, which is invariant as long as the temperature remains the same, or as long as as long as a catalyst is not introduced. If you introduce a catalyst, you get a different rate constant for the reaction. That is the result of catalysis. In fact, you can also have the reaction both catalyzed and uncatalyzed, and then you would add up together the two rate constants to calculate the sum of two reactions that are taking place through different mechanisms. Okay. And the second part of the question, 34, says, how do the half-lives of what quantity when graphed versus time will yield a straight line for a first order reaction? It would be ln of A sub T versus time. It'll give you an intercept B, which is corresponding to ln at time 0. Ln of A concentration at time 0. The slope of the graph, you'll get delta y or delta x. So here's the change in rise, and here's the change in run. Delta y versus delta x is going to give you the slope, which is equal to negative k, negative of the rate constant. The equation looks like that, and it's written in the form of y is equal to mx plus b. Here's the y component, here's the mx, and then the values of time are corresponding to the x coordinate of the graph, and there's the y-intercept. Now let's look at the next part of our notes, which is how to deal with second order rate data. Right? Second order plots, practice example 590. Okay. If you get second order plots, if you get second order rate data, to get a straight line, you have to plot it according to the following indications. You're going to plot ln of A sub T. 1 over A sub T versus time. That will give you a straight line with 1 over A naught as the intercept, and the slope in this case, m, will be delta y over delta x, and it will equal to positive k. So the equation takes the form of 1 over A sub T is equal to kt plus 1 over A naught. So again, it's in the y equals mx plus b format to get you the straight line. So if a plot of the data, Suppose you had a bunch of points and you plotted them according to this, and the points came out very close to a straight line. That would be an indication that you had second order rate data. If on the other hand the points came out looking like this or like this, you would have potentially first order or some other level of order. But when it's a straight line, it's second order rate data. Let's look at practice example on page 590. And it says, practice exercise. Consider the decomposition of nitrogen dioxide discussed in the sample exercise. The reaction is second order in nitrogen dioxide with a K equal to 0.543 molarity to the -1 seconds to the -1. If the initial concentration of nitrogen dioxide in a closed vessel is 0.05 molar, what is the remaining concentration after 0.5 hours? All right, so we're going to use equation 1414. So it's second order with respect to nitrogen dioxide concentration. So we can say 1 over the nitrogen dioxide concentration is equal to KT plus 1 over nitrogen dioxide concentration at time 0, where the nitrogen dioxide concentration is equal to 0.05 molar, K equals 0.543 molarity to the -1 seconds to the -1, and time is equal to 0.5 hours, or if you multiply by 3,600 seconds per hour, because you see the units of the K are in seconds, it turns out you have 1,800 seconds elapsed time. So let's plug in the values. This is probably where if you forget to do this step and just plug in 0.5 hours and it doesn't match the units of the rate constant, you're going to obviously get a wrong answer. So don't forget that step. Or always remember to look at your units to make sure they match, and if they don't, do the appropriate operation to get them to match. So 1 over NO2 concentration is equal to 0.543 molarity to the -1 seconds to the -1 times 1,800 seconds. This is the KT part, these two things, plus 1 over 0.05. Running out of room. So that turns out to be 1 over NO2 equals 977.4 plus 20. When you take the reciprocal of this, it becomes 20. So the answer is 997.4. So the NO2 concentration after 1,800 seconds equals, if you add up all that stuff together, you get you have to take, you add up all that, you get this, and then you take the reciprocal of it to get the NO2 concentration. So you get 1.00260678 times 10 to the -3 molarity. And after sig figs, you get 1.00 times 10 to the -3 molarity. There's your final answer for that question. Now let's look at half-life. Just have an unobstructed view for a few seconds, or you can pause and copy if necessary. Don't forget, I also have kinetics playlist that you can watch, where you have a full-sized board, and it was recorded many years ago. So if this lecture is not helping, or if it's not enough, you can watch those. I'm keeping it bare bones on this part. Obviously, you should read the book, like I always say. Now let's look at half-life. In an exponential decay, it is useful to know when half of a reaction has run its course, meaning half of the reactants have been used up. The practice of listing half-lives is common in the treatment of radioactive substances, because it's very important for scientists to know just how much radioactivity they're going to need to carry out certain operations. For example, if you want to irradiate somebody who has a cancer, you have to calculate the dose so that it kills the cancer without harming the cells, the healthy cells. When they were working at Los Alamos, a lot of their research centered around, Los Alamos was a place where all the top scientists of the world were racing to find the atomic bomb because they thought the Nazis were already working on it, and they were afraid the Nazis would take over the world, and so they wanted to prevent that. And so all the top scientists of the world rounded up, and they went to Los Alamos, which I think is in New Mexico, and they had a super secret facility where they all put together their best minds in the world to discover just how much uranium or plutonium or whatever radioactive nuclide they were using was necessary to get what's called a critical mass. Because in the case of second order decay, if you put large amounts of a radioactive substance together, it excites its own radioactivity, because when a radioactive nucleus releases a particle, those particles can go crashing into another nucleus nearby and elicit a radioactive event on the second nucleus. And if enough material is placed together in one place, you get what's called a criticality. And that's what they were trying to calculate. They were trying to find out how big of a piece of uranium or plutonium was necessary to achieve criticality. And they even had a few accidents where people lost their lives because they had some unsafe laboratory practices. But in the end, they generated two ways of detonating fissile material. One was called Fat Man, and the other one was called Little Boy. And they were two different bomb designs that worked around this premise that if you assembled enough radioactive material into one spot, the stuff gets a runaway reaction, chain reaction they call it, and it explodes and it releases an enormous amount of energy all at once. And the first design was basically to use a bowling ball sized piece of uranium but with a wedge missing, and the wedge was put on the other side of the bomb. When the bomb reached the height at which they wanted it to detonate, they would fire that missing wedge into the bowling ball sized piece that was missing the wedge, and when that wedge entered in, you had critical mass and the thing exploded. I think that was Little Boy. Fat Man had a different design where they put a critical mass of, I don't know if it was, I can't remember if it was uranium or plutonium, I think it was uranium, and they had it less concentrated than it needed to be to achieve critical mass, and then but they surrounded it with high explosives, so that when the high explosives on the outside detonated, it would compress that nucleus of fissile material to a small enough radius that it would achieve criticality, and that would cause an explosion. So that was called Fat Man, and both of those bombs were dropped on Japan. One was dropped on Hiroshima, the other one was dropped on Nagasaki, and both of them killed about 70,000 people each. A horrible event in the history of man. They shouldn't have done it, but they did it. Again, this is an example of what happens with when scientists who lack moral compasses start to make decisions based on, you know, okay, we can argue that they wanted to win the war and that the Emperor Hirohito wasn't giving up, but I don't know, I just can't get over the sneaking suspicion that they could have done things better. They were interested in testing out their demoniacal machine, and they succeeded in killing 140,000 people with it. Anyway, God's going to judge them, not me. Most of which decay with a first order curve. But it's not always the case. In case of radioactive nuclides, I think they decay in a second order curve. But let's look at first order first, because it's easier. Thus, if A is equal to A naught e to the kt in a first order decay, where A is equal to 1/2 A naught, and that's the half-life. At the half-life, half the stuff is used up. So that's what we're talking about, half-life. And K is a negative number because that's what you have with decay, for the value of K. Because it represents a decay. And then what we get is, by transposing the A naught, we get A over A naught is equal to e to the kt. We take the log of both sides, the ln of both sides, and we get a ln of 1/2, because remember, A is equal to 1/2 of A naught. So it's basically 1 over 2. It becomes 1 over 2. So ln of 1/2 is equal to kt, negative kt. Oh, I forgot the negative part there. So that means the half-life, T1/2, equals a ln, well, ln of 1/2 is 0.693, so what you get is 0.693 over K. This becomes 0.693. You want to isolate T1/2, you put that over here. So you transpose the K under, and 0.693 over K is your half-life in a first order process. Let's do an example of that equation's use. On page 592, practice example, it asks, using equation 1415, I guess the T1/2 is equal to 0.69 over K, 0.693 over K. It says, using equation 1415, calculate T1/2 for the decomposition of the insecticide described in sample exercise 14.7. B, how long does it take for the concentration of the insecticide to reach 1/4 of the initial value? So, here we go. What are we doing for time? 18 minutes. So, practice example on page 592. Part A. K equals 1.45 of a year to the -1. The insecticide concentration is equal to 5.0 times 10 to the -7 grams per centimeter cubed. And we want to know T1/2. We're told it's a first order process, so we can go straight to our little equation. And we get 0.693 over 1.45 year to the -1. That's the value of K. So it takes 0.477931034 of a year. Or if you like, 0.478 of a year. It's a little less than half a year. Another way of answering the question, because they say a quarter. Well, how does it take to do a quarter? Well, after one half-life, if you start out with 100% of the stuff, to get to 1/2, it's one half-life. To get to 1/4, it's a second half-life. So 2 half-lives in, you're at 1/4 of the original concentration. So 2 half lives, or 2 times t 1/2, which equals 2 times 0.478 of a year, gives you 0.956 of a year. So you get down to 1/4 of the concentration, it takes almost a whole year. I'll look at the full unobstructed view. And the next thing we're going to do is derive the half-life equation, or the half-life formula for second order process. But we'll start from the integrated equation of second order data. Go. So this is called derivation of half-life equation for second order reactions. Now we start off with our second order data equation. 1 over A at time t is equal to kt plus 1 over A naught times 0. We're going to transpose the 1 over A naught, so we're going to get 1 over AT. I can get rid of these square brackets just to streamline the calculations, otherwise it's going to get messy and take a long time. And I'm going to write a little bit smaller. So 1 over AT minus 1 over A naught is equal to KT. Then we're going to put them over a common denominator, which is going to be AT times A naught. And that's going to make the numerator A naught minus AT. How did I get that? Remember, if you have supposing you're subtracting or adding two fractions, supposing I want to add 1/3 plus 1/4, I would say 3 times 4 gives you 12. Now, how do I turn that 3 into a 12? I have to multiply by 4. If I do it to the bottom, I have to do it to the top. 4 times 1 gives you 4. And how do I turn a 4 into a 3? You got to multiply by 3. You got to do the same thing to the top. That's what I'm doing right here. Okay, so that's where I got that. So, but at t 1/2, A naught equals 2 times AT. So that allows us to make a little simplification. Substituting A sub t with A naught over 2, we get A naught minus A naught over 2 all over AT times AO. Why did I put 1/2? Yeah, because I took this and replaced it with A naught over 2. So this becomes also A naught. Because it was 1/2 A naught, I'm also multiplying this whole thing by 1/2. Alright, so there's a 1/2 in the denominator. And all this is going to still be equal to KT. And then what we'll do next is we will multiply these two things which are right next to each other. So this simplifies to the following. A naught. So if you have one A and you subtract half an A, you got half an A. So you got A over 2, A naught over 2, over A naught squared over 2 times K, because I've transposed the K. So that gives you the value of T, which by the way is going to be the T 1/2, because we just established that it's a T 1/2. I'm going to rewrite this equation like this. I'm going to say A naught over 2 times, flipping the denominator, 2 over A naught squared K. Can't partially cancel these, cancel this. So what you get is that it's equal to 1 over A naught K. So that's T, 1/2. So in a second order process, the half-life changes with respect to the rate constant and also the initial concentration. Like I was saying earlier, with radioactive nuclides, the more of the stuff you have present in one place, the more rapidly the reaction proceeds for whatever reasons. And in some cases, it's not even second order. It can be, I don't know, triple or quadruple order. I don't know how fast it can accelerate it. Oh my. Okay, so here we go. For homework, try this. Homework is 1434. It is a second order plot. Okay, and we'll see you on Monday. Have a good weekend.